from the proof idea. So get used to that. So yeah, we're starting now on a regular basis to prove theorems, and that's the nature of theory of computation. Remember, computers themselves historically are a kind of spin-off, kind of consequence of efforts to understand, to improve understanding in the foundations of mathematics. Right? There's an intimate link between mathematics, sets, and logic. Right? So it's not surprising that theory of computation is very pure mathsy, because it's always been that way since the very beginning, since computers, your general purpose programmable computers. That notion is a kind of spin-off, an engineering example, if you like, concrete example of Turing's universal Turing machine. Now, the UTM. Now, we will definitely talk about that in this course. It's in part 2, many chapters. There are only 2 chapters in part 1 basically on languages, automata and languages. Let me just check. So part 1, automata and languages, and there are only 2 chapters. Chapter 1 is regular languages. That's the one we're in the middle of a bit more now. And chapter 2 is context-free languages, a different category of languages. I assume not regular. But part 2 is 1, 2, 3, 4 chapters. And part 2 is computability theory. What can be computed. And in that part, we'll definitely do Turing machines and universal Turing machines. Really brilliant idea of Turing's that inspired a lot of people to think that it would be engineering-wise, technically possible to build such machines that could do what universal Turing machines could do. In other words, they could compute just about anything. Well, I say just about, because one of the points of part 2, given that the title of part 2 is computability, is something able to be computed. Can it be computed? Implying that sometimes some things cannot be computed, and there are famous examples of things that will never be computed, that no computer ever will be able to solve such questions. Right? So there's a lot of theory, a lot of pure math on computability theory. And part 3 is on complexity theory, and that's 1, 2, 3, 4. Also 4 chapters. Complexity theory addresses itself to those questions that can be computed, but some problems that can be computed, some are fairly easy to compute, and others incredibly hard and long and involve a huge amount of work. So the problems that can be computed tend to get classified into different families or according to what's called hardness. In other words, sort of the level of difficulty, the amount of time and effort, number of steps involved, logical steps, if you like, involved in solving such problems. And that's a major section, and a hot topic still very much in theory of computations. Working out all the math on what can be, the various levels of difficulty of what can be computed. Right. Okay. So we've finished with generalities. So theorem 1.45. Okay. Here's your theorem statement, proof idea, and then proof. And that's the pattern throughout the book. Okay. So the class or set, still not quite sure why. Sipser tends to use different words for a class, but anyway, maybe he gives a different definition to the word class as set. But so the class of regular language is closed, okay, under the union operation. And so we're doing this proof now for the second. Well, we're proving this proof statement for the second time, but this time using the non-deterministic approach. Okay, so what's the proof idea? Well, now you have two languages, Reg.Languages, which is just short for regular languages, of course. So you have two regular languages, A1 and A2, and we have to prove that the union operation is closed. In other words, A1 union A2 is regular. In other words, the result that you get applying an operator to a set, that result is also a member of the set. Okay? So if A1 union A2 is regular, then it belongs to this, that it too is a regular language. Okay? So it belongs to this set. So why does he call it class? Right. Okay, so what's the basic idea? And usually, noticing his pattern, the essential, the heart of his idea is in the basic idea portion of the proof, the first part, if you like. So the basic idea is that you take two NFAs, okay, call them N1 and N2, and N1 would recognize language A1, and N2 would recognize language A2. So you take these two NFAs, these two non-deterministic finite automata, these two N1 and N2, and you combine them. Like you incorporate N1 and N2 into a bigger NFA, call it N. See the diagram. Picture's worth 1,000 words. So here is your bigger machine, call it N, like N, right? And it consists of two smaller machines in a sense. N1, so here's your N1, that's your NFA N1, and N2. And the function of N1, its job is to recognize language A1, okay? And the function of N2, this NFA, its job, its function, is to recognize language A2, right? And the basic idea, well, besides that, is this. I'm jumping ahead a little bit, but you can probably guess at what's going to happen, right? So this is the starting state of N, big N. In other words, the machine N that is supposed to recognize the union of A1 and A2. Okay? Because if we can, now this is a proof by construction again. So if we can build a machine N that recognizes the unioned, if you like, language, so A1 union A2, then that means that language, A1 union A2, has a finite automaton, N, big N, which is an NFA that recognizes A1 union A2, right? And therefore, since such an automaton exists, therefore that unioned language, A1 union A2, it is a regular language, right? Because it has some automaton that recognizes it by definition, right? And that's true for any two languages, A1, A2, belonging to the whole set of regular languages, and therefore that set of regular languages, class if you like, is closed under the operation union. Hope you follow that. Okay, so again, it's a proof by construction. Right? We actually build the thing, we design it. Yeah. Okay, so it has two. This big N. It has two components, like N1 and N2. N1 recognizes A1, N2 recognizes A2. Now, if N1 happens to detect A1, then N will. Okay? We designed it in such a way that happens. And if N2